Hello students, in this module let us discuss about geometrical isomerism. This is useful for the students of grades 11th and 12th. Please subscribe my channel, like, share and comment my videos. Stereoisomerism. Stereoisomerism is of three types. One is conformational analysis, geometrical isomerism, and the third one is optical isomerism. Now, in this module, let us discuss about geometrical isomerism. So, geometrical isomerism. Geometrical isomerism. Now, let us start with an example C4H8. C4H8. What is this substance? This is butene. What are the structures, possible structures for this butene? This is CH2CH double bond CH3. This is but1ene. Let us say this is structure 1, and the other substance CH2 double bond CH2 CH3. This is but2ene. This is but1ene. So this is structure 2. Now the other substance with CH3 C double bond CH2 CH3. This is isobutene, or it is referred as 2-methyl propene. Now here structures 1 and 2 are position isomers. Position isomers means they differ in their double bond. Structures 1 and 3 and 2 and 3. These two pairs are chain isomers. In structure 1, 4 carbon atoms are there in single chain, and in structure 3, 3 carbon atoms are there in single chain. So structures of the pairs of structures 1 and 3 and 2 and 3 are chain isomers. Now it is observed that the structure 1 has another isomer depending on arrangement of atoms. How the atoms are arranged? See, this is a doubly bonded carbon atom. So this is hydrogen, and here this is a CH3. This is hydrogen, this is CH3. So this is one arrangement. Here the atoms are groups of atoms. Hydrogens are atoms and CH3 are methyl groups of atoms. Now for this another arrangement, molecular formula is same, HCH3 on second carbon, and here hydrogen, this is a CH3. So here two structures are possible. This is structure A, this is structure B. So in the structure A, the same groups or atoms are on the same side. So same groups or atoms are on the same side. Here same groups same groups or atoms are on opposite sides of doubly bonded carbon atoms. So here the spatial arrangement is different. So such an arrangement in which the spatial arrangement of atoms or groups differ is referred as a geometrical isomerism. Now in conformations, rotation around CC single bond is possible. The reason here is from one spatial arrangement to another arrangement, the energy required is only 12.5 kilojoule per mole. And of course this amount of energy is obtained even at normal temperature. Therefore conformations are possible at normal temperature. Hence the conformations are in a dynamic equilibrium. Therefore the conformations cannot be isolated from each other or cannot be separated from each other. Whereas CC double bond rotation is not possible. Why rotation is not possible? The pi bond hinders the rotation. If we apply high amount of energy and tries to rotate, then pi bond breaks. So if the rotation is possible, rotation is brought out, the pi bond breaks. So for breaking the pi bond, the energy required is nearly 245 kilojoule per mole, and this amount of energy is not obtained at normal temperature, not obtained from atmosphere at normal temperature. Therefore the rotation of a CC double bond is not possible. So as a rotation of CC double bond is not possible, the arrangement of groups or atoms differ in different substances. Hence such an isomerism is known as geometrical isomerism. So in this geometrical isomerism, let us take the previous example once. So this is the previous example. Let us write this example once again. So this is CC double bond and hydrogen here, methyl group, hydrogen here. This is a methyl group and hydrogen. So same groups are on same side. Therefore this isomer is referred as cis isomer. Cis means same groups are on same side. On the other hand, other isomer C double bond C, hydrogen CH3, this is hydrogen CH3. So same groups or same atoms are on opposite sides. So same groups or same atoms are on opposite sides. Therefore this isomer is known as trans isomer. So cis isomer and trans isomer. Now what is cis isomer? Cis isomer means an isomer in which the same groups or atoms are on same sides same sides of the doubly bonded carbon atoms, whereas trans isomer is that in which the same groups or same atoms are arranged on opposite sides of the doubly bonded carbon atoms. Therefore, this isomerism is also referred as cis-trans isomerism. Cis-trans isomerism. So for this cis-trans isomerism, what are the conditions? The conditions for cis-trans isomerism. Conditions. So the conditions are, number one, there should be a doubly bonded carbon atoms. There should be a double bond. There should be a double bond. The first condition. And the two groups are atoms. The two groups are atoms attached to doubly bonded carbon atoms. Doubly bonded carbon atoms should be different. Should be different. Right. For example, if say this is double bond C, this is CH3, hydrogen. What is this substance? This substance is propene. This substance is propene. On this propene, the first carbon, the C1 carbon has two similar groups, two same groups. In such case, cis-trans isomerism or geometrical isomerism is not possible. Therefore, the third condition is even on one carbon atom, if atoms or groups are same, then geometrical isomerism is not possible. Geometrical isomerism is not possible, or cis-trans isomerism is not possible. Now the geometrical isomers differ in their physical properties, physical properties like melting point, boiling point, dipole moment, solubility, etc. And the chemical properties are similar but not identical. So physical properties differ in properties like melting point, boiling point, dipole moment, solubility, etc. Whereas the chemical properties are similar but not identical. Now let us see, for example, cis isomer. Cis isomer is more polar. Cis isomer is more polar than trans isomer. Why? If you see this diagram, you can understand. For example, this is a butene, CH3, hydrogen, CH3, hydrogen. So here the dipole acts in this manner, whereas dipole acts in this manner. Therefore, the resultant dipole is not zero. Resultant dipole moment is not zero. Resultant dipole moment is not zero because they are not acting in the different directions. In cis isomer, the resultant dipole moment is not zero because the dipoles act not in different directions. Whereas in trans isomer, this is trans isomer, CH3, hydrogen, this is hydrogen, CH3. So here the dipoles act in this direction here and of course act in this direction. Therefore the dipoles act in different directions. As the dipoles act in different directions, the dipole moment dipole moment mu, right? And dipole moment mu is equal to 0, whereas here the dipole moment mu is not equal to 0. Thus, the dipole moment in cis isomer is more than trans isomer. That is, cis isomer is more polar than trans isomer. So, because of the dipole moment, boiling point of cis isomer, cis is greater than trans isomer. Boiling point of cis isomer is greater than trans isomer. On the other hand, melting point of trans isomer is greater than cis isomer. Why it is so? In trans isomer, the molecules, the close packing of molecules is possible. Therefore, because of the close fitting, it needs more energy to separate them from each other. Thus, the trans isomer has a more melting point of trans isomer is more than that of cis isomer, whereas boiling point of cis isomer is greater than trans isomer because of the dipole moment. Now let us see one example. Of course, assign cis trans configuration to the substance. So here, what is this substance? C double bond C, CH2CH3 hydrogen. This is CH3. This is hydrogen. First of all, give the name to this substance. What is the name of this substance? Give the numbering to the long chain 1, 2, 3, 4, 5. So this is pent-2-ene. The name of the substance is pent-2-ene. Now, and this pent-2-ene, same groups, that is hydrogen and hydrogen are similar, same groups are on the same side. Therefore, this is cis pent-2-ene. On the other hand, if you reverse this C double bond C, this is CH2CH3 and of course hydrogen here, and of course let us keep this CH3 on this side. This is hydrogen. So what is this isomer? This is same groups are on the opposite sides. Therefore, this is trans pent-2-ene. So in this type of substances, one set of groups or atoms are not same, but even then the other set of groups or atoms are same. Therefore, we can assign a cis trans configuration to such a pair of substances. Now let us see another example. This is CH3 hydrogen, and of course hydrogen here. One phenyl group is there. So what is the name of this substance? 1, 2, 3. 1, 2, 3. So phenyl group is present on first carbon. Therefore, this is phenyl propene or phenyl prop 1-ene. So as same groups, that is hydrogen atoms are present on the same side. Therefore, this is cis phenyl prop 1-ene. Suppose if the substance is present in this manner, C double bond C, this is a phenyl group, and of course this is a hydrogen. CH3 group is on this side, and this is a hydrogen. So if the hydrogen atoms, that is same groups, are on the opposite sides, therefore this is a trans isomer. Trans phenyl prop 1-ene. Now let us see this example. This is C. This is hydrogen, fluorine, chlorine, bromine. So what is this substance? Name of the substance is 1-fluoro 2 chloro, 2 chloro, 2 bromo, 2 bromo, ethene or ethylene, ethene or ethylene. Just find out whether any one of the carbon atom has the same set of atoms or groups. So in this example, all 4 groups are different. All 4 groups are different. All 4 groups are different. In such case, how do we assign? So in this case, cis-trans configuration is not possible. Cis-trans configuration is not possible. Cis-trans configuration is not possible, but a similar one, similar to cis-trans configuration can be assigned in this case. Then what should we do in such case? So here, in this case, a similar configuration to cis-trans can be assigned. Cis-trans can be assigned here. So what is this? So such a configuration is referred as EZ configuration. EZ configuration. So in this EZ configuration, the groups must be assigned priority. The groups must be assigned priority. Priority groups must be selected. So priority groups must be selected. How to select the priority groups? So we have to follow certain rules for selecting the priority groups. So the atoms directly attached to CC double bond must be checked with atomic numbers. The atoms that are directly attached to CC doubly bonded carbon atoms must be checked with atomic numbers. So here in the above example, this is hydrogen, fluorine, chlorine, bromine. So on the C1 carbon atom, chlorine and bromine, what is the atomic number of chlorine? 17. Atomic number of bromine is 35. Therefore, bromine has a higher atomic number. Therefore, this is a priority 1. So what we have to check here? The atom with large atomic number or greater atomic number. The atom with greater atomic number must be given priority 1. And of course, automatically the second group with less atomic number or smaller atomic number gets the second priority. So on the C2 carbon atom, fluorine has atomic number 9, whereas the hydrogen atom has atomic number 1. Therefore, fluorine is the priority 1. So here, priority groups are on opposite sides. Priority groups are on opposite sides. As priority groups are on opposite sides, so the isomer with priority groups on opposite sides is assigned E configuration. E for opposite means opposite. So if the priority groups are on the opposite sides, then it is E configuration. If the priority groups are on the same side, priority groups are on the same side, it is Z configuration. Z means same. Z means same. So in this way we can assign a EZ configuration if the substance does not have the same groups or same atoms on either side. So EZ configuration, E configuration is assigned to such an isomer with priority groups are on the opposite side. Z configuration is assigned to such an isomer if the priority groups are on the same side. Now let us see one more example. One more example. This is CH3, CH2, C, Cl, double bond, CH, Br, CH, Br. Now double bonded carbon atom CC, here on one side hydrogen, on the other side bromine. For chlorine on one side, for this carbon, chlorine on one side and CH2, CH3 on the other side. So here what happens in this group has two atoms. In such case always we have to see the atomic number of the first atom which is directly connected to the doubly bonded carbon atom. So here atomic number of hydrogen 1, atomic number of bromine is 35. Therefore this is a priority group, priority 1. Whereas here chlorine atomic number is 17, atomic number of carbon is 6. Therefore chlorine is priority 1. So here priority groups are on the opposite sides. Therefore this is trans isomer. What is the name of this substance? Number 1, this is number 1, 2, 3, 4. So this is bromine is present on first carbon, 1 bromo, 2 chloro, 1 bromo, 2 chloro, but 1 ene. 1 bromo, 2 chloro, but 1 ene. So this is the name of the substance, and of course this is trans isomer. If the groups are altered, then it becomes a trans isomer. Now let us see a typical example. So this is a bond line formula, double bond here. So here in this manner. So here chlorine. Now first of all, if such a bond line formula is given, write the normal structure. So first of all, in such case, what you have to do, first of all you write C double bond C. So here chlorine atom is present down below, therefore here chlorine. And how many carbon atoms are here? 1, 2, 3. So here CH3, CH2, CH2, CH3. And for this, the above one is isopropyl group. So this is CH3, CH3, this is CH2. Right. So here this is CH2, CH3. Now of course, first of all, select the priority group. On the C1 carbon atom, this is C1 carbon atom. On C1 carbon atom, this chlorine C1 has chlorine on one side and of course propyl group on another side. Always, even if the more than one atom is present, always you have to check the atomic number of the first atom which is directly connected to the doubly bonded carbon atom. So the first atom is here chlorine. Chlorine has atomic number 17, whereas here carbon atomic number is 6. Therefore this is priority group. Chlorine is the priority group. Now come to the C2 carbon atom. In C2 carbon atom, the first atom is carbon here also carbon. So first atoms are same. If first atoms are same, then you have to check for the second atom. The second atom is also carbon here. Second atom here is carbon. Second atoms are also same. Then if the first and second atoms are the same, that is they have the same atomic number, then you have to look for the third atoms. What are the third atoms here? Hydrogens. Whereas the third atom here is carbon. So third atoms are different. As third atoms are different, you have to give the priority based on the atomic number of the third atoms which are connected to the doubly bonded carbon atom. Therefore, isopropyl has a priority 1. Priority 1. So here priority is chlorine and priority is isopropyl. So priority groups are on the opposite sides. As priority groups are on the opposite sides, therefore this is a trans isomer. This is trans isomer. Now, what is the name of this substance? The name of the substance is 1. This is number 1 carbon, number 2 carbon, number 3 carbon, number 4 carbon, 5, 6, 7. Therefore, this is hept. Hept. The double bond is present on first, second, third. Hept3ene. Hept3ene. So the long chain is hept3ene. On the hept3ene, what are the groups present? The groups present, the chlorine atom is present on the 4th carbon. Therefore, this is 4 chloro, and this is ethyl group. Ethyl group is present on 3rd carbon, 4 chloro, 3 ethyl. Methyl group is present on 2nd carbon. Therefore, this is 2 methyl. So, this is 4 chloro, 2 ethyl, 3 ethyl, 2 methyl, hept3ene, and of course, this is a trans isomer. So, here this can be referred as trans isomer, or otherwise, what is the, as per EZ configuration, priority groups are on the opposite side. Cis-trans isomerism can be compared with EZ configuration. So here in this structure, the priority groups, priority 1 here, priority groups are on opposite side. As priority groups are on opposite side, this is E configuration. E configuration is similar to trans isomer. So here also the priority 1 here, the priority groups are on opposite sides. As priority groups are on opposite sides, this is a E configuration. As priority groups are on opposite sides, this is E configuration. E configuration is similar to trans isomer. And of course, cis-trans isomerism is observed even in cyclo compounds also. Let us see one such example. So this is cyclopentane, hydrogen Cl, and of course this is hydrogen Cl. So in cycloalkanes, double bond is not present, but because of the cyclic structure, the rotation is not possible. Rotation about the CC, single bond, is not possible because it is a cyclic structure. So in this structure, the same groups are on the same side. Same groups are on same side. Therefore, this is a cis isomer. What is the name of the substance? Cis 1,2-dichlorocyclopentane. Cis 1,2-dichlorocyclopentane. And here, this is another isomer. This is hydrogen chlorine, and of course this is chlorine hydrogen. So here the opposite groups are on the same groups are on the opposite sides. Therefore, this is a trans 1,2-dichlorocyclopentane. Therefore, geometrical isomers are those in which the different substances having the same molecular formula but differ in their spatial arrangement with respect to doubly bonded carbon atoms is known as geometrical isomerism. It is also referred as cis-trans isomerism. Cis-trans isomerism is possible when the same groups, sets of same groups are present. If sets of same groups are not present, even then we can assign the configuration, that is EZ configuration, depending on the priority of the groups attached to it, to the doubly bonded carbon atoms. Assign the E configuration or Z configuration to the compounds given here. In the next module, let us discuss optical isomerism. Please subscribe my channel, like, share, and comment my videos. Thank you.